In the previous lecture, we were talking about discrete convolution. We looked at three different ways of doing it. Actually, we looked at one way completely, which was the analytical approach. And we were kind of in the middle of the second approach to perform discrete convolution, which was an array-based algorithm. Very structured, um, probably the easiest way to perform discrete convolution, and works very well in the case of uh, finite sequences, maybe a few elements at a time. So if you have, say, sequences in X and H, say 5 elements in X and 6 elements in H, a few that you can even count on your fingers, then the discrete convolution, array-based discrete convolution works out very well. So what does it involve? It involves distributing the elements in one of the inputs on the columns and the other discrete signal, in this case, on the rows. So H of 0, H of 1, H of 2, H of 3, H of 4, those are 5 elements in H that are written up in that particular column here that correspond to the five rows. And similarly, we have 5 elements in X, X of 0, X of 1, and so on. Those are laid out for each of the 5 columns here. And to compute the cell, all you have to do is perform that multiplication operation. So for example, the first column here corresponding to first row, first column is X of 0 multiplied by H of 0. Similarly, you would multiply each corresponding row and column and you would fill out this entire array. And once you fill out the entire array, we need y of n, right? So we need the output when the input is x and the h impulse response is h. So to compute the output, all you would have to do is sum across the diagonal. So we were talking about this slide when we stopped, where to compute y of 0, and I hope you see that y of 0, the index is 0 here because the sum of the indices for x and h is 0 and 0. So you sum across that just one element, you get y of 0. Similarly, for y of 1, you sum across that diagonal there. The index is going to be 1 because 1 plus 0 equals 0 plus 1. You get y of 1. And similarly, you get all the other elements up until y of 8 by summing across, indicated by that summation sign, across that diagonal. And the underlying math is directly connected to that convolution summation that we derived in the last class, which essentially relates to superposition. And superposition is the superposition principle relies on the system being linear and time invariant. So we went from linear and time invariant systems to the fact that we can apply superposition on them to discrete convolution. All right, let's keep moving. This is again the same array in which we are shown the diagonals being computed. Next, let's work through an example here. The example in which we are seeing right now is we have an input x. Well, I don't even know it's an input. I'll just say one of the signals, discrete signals that we need to convolve is x with 5 elements, and the underline is indicating that corresponds to n is 0. The elements are 1, 2, negative 1, and so on, and those are distributed in that top row over there. And then the second discrete signal h, the elements are also given, is distributed on that column here, h of n, h of 0, 1, 2, and so on. And once you do that, you simply multiply each corresponding row and column. So for example, to get the first one, you would multiply that, and we can take any arbitrary row and column here. Say for example 15, you would multiply 3 and 5 and get that. You would run through all the 25 cells in this case because you have 5 elements in X and 5 elements in H. And once you do that, you have laid out the array. Once you lay out the array, you sum across the diagonal. And let me erase these two so that I worry about how to sum up the diagonal. So let me indicate the summation in black here. So I would do a summation this way, and a summation this way, a summation this way, a summation this way, and that. All of them are being summed up. So what do I get? I get my answer in, say, pink. Y of, what is the index there? The index would be 0 plus 0. So y of 0 is, what are the elements being added? Just 1. Negative 1 is the answer there. Y of 1 is negative 2 because 0 minus 2. And then similarly, I can fill up the entire output sequence here. 2 plus 1. 9 minus 3. And here you have 10 minus 2. Here you have got, let's see, 2 minus 3 here. 17, 4, negative 16, 4. All right, so I hope you can combine that and then simply write out the result. Y of 0, so let's write the result here. Y of n, negative 1, and I'm going to put an underline because that corresponds to n is 0. Then negative 2, 3, 6, 8, negative 3, 13, negative 16, and 4. Now, I want you guys to kind of look at a few things here. We will be proving some of these properties later on, but I want you to start recognizing certain patterns given the signals that you are trying to convolve and the output sequence. How many elements are there in the output sequence? I should say non-zero elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 elements in the output. Is that number related to the number of inputs and the number of signals, the number of elements in the signals that are being convolved? Yes, it is directly related. Because here you have 5, here you have 5. So you add up the number of elements in the first sequence and the second sequence and subtract a 1, that will be giving you the number of elements in the output sequence. Now, a few things to note here. There are zeros to the left of -1, there are zeros to the right of 4, so those are not being counted in this 9. Another thing to note over here is there could be a 0 in the middle of this y of n sequence if the addition works out that way. So if there is a 0 in the middle here, that is being counted in that 9. Number of inputs, so A is indicating the number of elements in X, and B is indicating the number of elements in H, and then there is a -1. So it's the number of elements. The second thing I want you to note is at what values of n does the output start and stop. So over here, this guy is at n is 0, and it stops when it is what? If it is 0, 1, 2, 3, 4, 5, 6, 7, 8, n is 8, right? Are those limits related to the limits on the two signals being convolved? Yes, they are. This corresponds to 0. This corresponds to what? 1, 2, 3, 4. N is 0 there, N is 4 there. N is 0 there, N is 4 there. So for the lower limit on the output is the sum of the lower limits on X and H, and the upper time limit is the sum of the upper time limits for X and H. So those are the two things that I want you to recognize in this particular example, which will prove very useful later on. We talked about the number of elements in the output and the limits on the output and how they are related to the input sequences. The inputs meaning the input signals being convolved. All right, let's move on here. I want to talk about graphical approach next, but in order to do this, I have made a sort of an animation, PowerPoint animation. So it doesn't appear very well on the slide. So I will try to show that in PowerPoint here. Let me change. This one is this guy. All right. I hope that you are able to see the screen that I'm sharing right now. If somebody can quickly say yes, I can keep moving forward. Thank you. On the top here, I have y of n equals x of n being convolved with h of n. And that can be written up in the discrete summation, the convolution summation, as over here. Summation m equals negative infinity to infinity, x of m, h of n minus m. Now I have color coded them as blue and red to indicate the input and the impulse response of the discrete time system in red. I have arbitrarily chosen x and h in the plot on the left here and on the right here. So I have arbitrarily chosen x of n to be 5 ones starting from n equals 0 to n equals 3. So this is essentially u of n minus 4. So you can write that x of n in terms of step sequences. In any case, those are just 4 ones. The rest of the elements are 0. That needs to get convolved with h of n, which is 5 ones starting from n equals 0 all the way to n equals 4, which can also be represented using step sequences as u of n minus 5. Now, in order to indicate certain aspects about this convolution, I have provided a color code for the samples in H, a light shade here, and as it goes to the right, there's a dark shade there, and it is for a purpose. Now, what do I need in terms, if you look at the summation formula, what do I need? First, I need x of m, right? So how do I go from x of n here to x of m? Well, just change n to m. So if you change n here, n to m here, n to m here, you get the same sequence. So x of m remains as is. How about h of n minus m? So right now I have n. First I need to go to m, h of m. I have done that. I went from h of n to h of m. Do I need h of m? No, I need h of minus m. So I need to flip it about the vertical axis. So I hope you can see that the outer darker elements went onto the outer side. So h of minus m is flipping h of m about the y-axis, about the vertical axis. What is the next step? The next step is kind of the most crucial one here, which is to add another variable n to this. When you add another variable n to this, what would happen to the time limits? Over here you have 0, -1, -2, -3, -4. And on the right side you have 1, 2, 3, 4. What would happen to those times when you go from h of minus m to h of n minus m? Well, everything will be added, right? N will be added to everything. So that's the next step. So 0 became n, -1 became n minus 1, -2 became n minus 2, and so on. And then we got h of n minus m. Over here we are sketching this with the same m as the independent variable, the horizontal axis. So you have x of m on the left, you have h of n minus m on the right. All we need to do is multiply these elements and add them up, right? So multiply these elements and add them up. So what do we need to do here while you are adding them up? So for example, if you look at y of 0, if you needed y of 0, what would you do? You would do summation m equals -infinity to infinity, x of m, h of 0 minus m. What would 0 minus m be? 0 minus m would be, all these are 0. So instead of n, it is 0. Instead of n minus 1, it is -1, and -2, -3, -4. And at that time, what would you do? You would multiply these two things and add them up. So when you multiply those two things and add them up, you would get only one element that is common, 1 times 1. That's it. So y of 0 will come out to be a 1. But you would need y of -1, you would -2, -3, -4. Y of +1, +2, +3, +4. So as you are changing small n, you are essentially shifting h of n minus m from all the way to the left to all the way to the right in integer time steps. And as you are moving things from left to right in integer time steps, you are multiplying the two signals and adding the results up. So I can indicate that movement from left to right as that. So I hope that that was a helpful discussion there. Let me switch the mode here. All right, so we are back to our PDF slides that we are writing on. So all of that animation is being represented over here, right? Let's walk through step by step next. And we are focusing on things that are mainly giving you some non-zero output. So for example, I'm going to leave x of m as is, and I'm going to consider h of -1 minus m, 0 minus m, 1 minus m, and so on. I would have several to look at. And I hope you see that as I'm changing this element here, -1, 0, 1, and so on, I am effectively moving things from left to right in the sequence. And that movement is in integer time steps. When n is very negative, like -2, -3, -infinity, you don't have any common elements to multiply, so you are going to effectively get a 0 for the output. I don't even need to bother. But let's start with y of -1. Y of -1 is, n is -1, so you are doing h of -1 minus m. being multiplied with x of m, and once after you multiply, there are going to be a lot of elements in which you are not going to have any overlap between h of n minus m and h x of m. But if you start looking at y of minus 1, which is, it is y of minus 1, so n is minus 1. N minus 1 corresponds to h of minus 1 minus m, which is one time step to the left compared to h of minus m. There is no common element between that sequence and x of m. They are completely at different times. So that summation would evaluate to 0 because the product is 0 for all the elements. Next, when you move down this list, you are essentially going from -1 to 0 to 1 to so on, right? So you're essentially moving this right one time step, one integer time step. And as you are doing that, you are evaluating the product of overlapping elements. So here there is one overlapping element. Next, there are two overlapping elements with x of m. And as you are evaluating that product, this essentially goes from 0 to 1 to 2, and you may probably able to guess, as you are moving this more to the right, you are going to get three common elements here, three overlapping elements. So your product goes 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. And then you do one more step to the right to evaluate y of 3. You have 4 there because now your all 4 are going to match up. So you have 1 times 1 4 times, you add them up, you get 4. And when you move one more to the right to evaluate y of 4, because h of n has 5 ones, only 4 of them can overlap at a time. So over here, these 4 will overlap with these 4. But the last one doesn't overlap. So you still get 4 here. Continue moving to the right. One time step at a time, one integer time step at a time. And as you're doing that, you go down from 4 to 3 to 2 to 1 to y of 8 will be 0, y of 9 will be 0, and so on. It will not have any overlap. So all of that can be sketched using this. If your sequence x of n is the one that is shown in blue here, and you have an impulse response shown in h of n in red over here, when you convolve these two signals in discrete time, you get y of n to be this triangle looking waveform. And all of these are essentially for each time step, for each integer time step, we have evaluated that in the previous example. So time steps, we just looked at that. When you, how many elements are there in the output y? The non-zero elements, you got 1, 2, 3, 4, 5, 6, 7, 8. Those 8 can be related to the input sequences as 4 plus 5 minus 1. You get 8 of those elements. Other things to notice: first non-zero element at 0, which is 0 plus 0. The last non-zero element 7, which equals 3 plus 4. Let's move on and summarize the graphical approach in a stepwise manner. Plot the signal x of m versus m. So when you start with x of n, switch the time variable to m, essentially leaving one of the signals unchanged. We will later look at the fact that convolution is commutative. so it doesn't really matter which one you do first. Next, we have plot signal h of n minus m. For this, you would start with plot of h of m, then you would flip it about the y-axis to plot h of minus m, then you would plot h of n minus m by adjusting the time values, essentially adding n to all the integer time values. And then once you are ready with h of n minus m, you are essentially ready with this piece. And when you're doing h of x of m, you are ready with that right away. And then you can slide h of n minus m across x of m in integer time steps from left to right. And at each time step, integer time step, you would try to multiply the overlapping elements and you would add them up. So that's essentially how you evaluate the discrete convolution. Let me